All is good? Yes. Okay, good morning, everybody. So thank you for being here in this session, this biorefinery session. I have to say that I hope that you're ready for a very eclectic session because we're going to blend some mushrooms with some medical applications on XYLANS and with some green methanol. I'm not sure what we're going to get out of this in terms of the mix, but I'll hope a nice cook. So we'll start first with the work of Luis Alejandro Romero-Soto, deciphering biorefinery valorization routes for spent mushroom substrates, enzymatic saccharification, lignin recovery. So Luis is a chemical engineer with a PhD in biotechnology from London University, Sweden, and is currently a researcher at the University of Inland, Norway, focusing on biorefineries and bioreactors. So, Luis, nice to hear you. Let's see.
Thank you so much. Okay, I'm assuming that this is audible, right? Okay, perfect. Yay. Okay. So first of all, I am very thankful to have this opportunity to present what we have worked with in this project. The title is a bit long, but of course we will just focus on the main actor in our project. That almost by design is the central word in that long title. That is the mushrooms. So, first of all, we have the overview of the presentation. I'm going to just give a short introduction. I'm going to present the goals of the study, the how we achieved those results, those goals, the results, conclusions, and perspectives, and of course, the acknowledgements. As for the introduction, so what does this beautiful picture tell us? Is that unlike men, mushrooms are not born equal. And that means that we can find mushrooms that perhaps find their applications in the medical field. And some of them we just eat. But unlike some other ingredients that we find in the food industry, we obtain the mushrooms in a different manner. To your right, you can see a time lapse of how we obtain the mushroom. Time lapses are an amazing tool because you can actually see a nice visualization of how a process transforms the initial substrate. But of course, we're going to focus not only on the edible part, that of course has some interesting features, being climate smart, being very versatile as for the substrate, or being a rapidly growing market. But rather, we're going to focus on the SMS, what is left behind after the cultivation. The SMS, that is short for mushroom spent substrate, is actually something that we produce a lot of whenever we're cultivating mushrooms. We are going to produce around 3 to 5 kilos of SMS per each kilo of mushroom, meaning that the disposal of this sometimes is going to be quite challenging. But of course, this is also biorefinable. Let's take a closer look. What do we know so far about spent mushroom substrate? Of course, this is not a blank field. It's something that has been researched. And an interesting thing is that some of the light that we have shed into this project is actually already published in various journals, and we have focused on highlighting what we do know and what remains to be known. And of course, this is kind of what research looks like. You have to probe into the darkness and sometimes shed light in a very small place, but that small place can actually make the whole difference. These are the goals of the study. We studied the composition of different types of SMS. We analyzed the efficiency of enzymatic saccharification. We explored lignin recovery, and we developed a framework of biorefineries surrounding SMS. How we did this? Of course, you can see the project summarized in this nice picture. This is almost poetic because you can see that if you read the graph vertically, you're going to get some processes that arrive at some final products. As for the mushroom cultivation, you get the fruit bodies. As for the SMS, you can arrive at biofuels, biopolymers. From the saccharification residue, you can get some functional materials, and from the extraction residue, you can find lignin. But of course, if we read the graph horizontally, we arrive at something quite interesting, because from each of these processes, you can actually identify some side streams. In the case of the mushroom cultivation, you have one main side stream, that is the SMS. In the case of the enzymatic saccharification, you get the residue. And in the case of the extraction, you get its residue. Each one of these can be further valorized. But of course, we have to focus on something very important at this point, and this is the SMS. I told you that not all mushrooms are born equal, and that applies for the SMS as well. So we carried out the study with two types of SMS. One that derives from the cultivation of shiitake mushroom, and then that derives from the cultivation of Pleurotus ostratus mushroom. So what we do know that they have in common is that they are composed of this marvelous puzzle that is the lignocellulose. But of course, if we know how to put together a puzzle, we of course know how to deconstruct it. Once we deconstruct this puzzle, we are going to identify that each one of the fractions can actually be separated by different procedures. And the procedures that we use in this current project are the ones that you see highlighted: the biological, the hydrothermal, and the dilute acid. Once we arrive at the post-saccharification, of course, what we are left with is something that is rich in lignin. And in this project, we use an interesting solvent that is called gamma-valerolactone to kind of solubilize and then recover part of that lignin. And of course, this is what makes the project interesting, because we are attacking all the potential components that we have in this spent substrate. Some of the results that we arrived at: here we have a nice graph where you can actually see the digestibility of each SMS species. In the case of shiitake, both for the cellulose and the xylan, you can actually observe that we have higher results compared to the oyster mushroom. And actually, this is what gave us the hint that this SMS could actually be used directly in the enzymatic saccharification. But as opposed to this one, the oyster SMS, we needed to do something else to it in order to arrive at such good results. So what we did to it is that we subjected it to HT treatment, meaning that we use an equipment that is called a power reactor, that is essentially a pressure boiler. So we worked at 175 Celsius degrees, and in two types of situation: non-isothermal, meaning that we just arrive at the temperature and then we cool it down, or partially isothermal, meaning we heat it up to 175, we wait the 30 minutes at that temperature, and then we cool it down. And of course, the results are quite emphatic, because you can observe that the raw SMS compares very poorly to its competitors. In this case, that is the SMS that was treated non-isothermally and the partially isothermal. That is the takeaway message. That is, the HT treatment actually enhanced the enzymatic saccharification. An additional thing that was interesting to analyze was to compare how the sugar concentration evolved during time. And we arrived at an interesting conclusion here, is that if you observe the graphs, you can actually see that up to the 24 first hours, you actually get around 85 to 90% of the total sugar content that you're going to be arriving at the 72 hours. And that actually is quite interesting, because it teaches us that we can actually shorten the enzymatic saccharification process. And this is very interesting if one thinks about an industrial perspective. And finally, we have some results for the lignin solubilization and regeneration. We have observed that in this case, lignin recovery was more efficient when we arrive at a higher solubilization. And of course, this is also something that is quite interesting to highlight. So, some conclusion and perspectives in this case. Now, just a short anecdote. I remember that when I was doing my PhD, one time I had a meeting with a supervisor, and she told me, Alejandro, do you know what do I do whenever I have trouble sleeping? And of course, I was naive, and I asked. And she told me, I read your conclusions. So I learned the hard way that science has to be concise, but it also has to be exciting. It has to be captivating. So we're going to give it a try. We're going to focus that the shiitake spent mushroom cultivation actually can be a very interesting strategy as a biological pretreatment. That the hydrothermal pretreatment, in this case, can significantly improve the biorefinery and the lignin recovery, and that the feasibility of developing circular bioeconomy systems can actually be based on the mushroom spent substrate. But let's take it beyond. One step beyond means that we are just going to focus on these two terms, spent mushroom substrate and circular bioeconomy. We can start from something that may well be discarded by many companies, but of course, we scientists know better. And in this case, we can see that the possibilities for this residue are kind of endless. We can produce or we can extract some interesting molecules, we can derive lignin from it, and we can directly obtain fermentable sugars. And these fermentable sugars can be transformed into many things, bioenergy, biofuels, or even biomaterials. And actually, if you want to learn a bit more about biomaterials or bioplastics, we have an interesting poster right outside that focuses on the next part, that is transforming these SMS into something as interesting as bioplastics. And of course, this is MUSA certified. That is the name of the project, Mushrooms for Sustainable Agriculture. Now, as for the acknowledgements, that is a translation of a great team is normally behind every successful project. This is the paper that this research is based on. We have two researchers here. We have Sarah, that is the main researcher, and we have our project leader, that is Carlos. And they are, of course, very well highlighted here in this picture. If you cannot find the guy that is talking to you right now, I am there in a cartoon form. And of course, what we have to remember is that whenever you have a bad day at the lab, you only have to remember this, that impossible only means you have not done enough research yet. Thank you very much.
So thank you, Luis, for the very nice presentation, concise and time-wise. So we'll go for the next presentation, Unlocking XYLANS Value Through the Development of Fully Bio-Based Materials for Diverse Applications. This is coming from José Silva. José is a PhD student, currently finishing his PhD in Chemical Engineering at the University of Aveiro. His research focuses on the development of novel xylan-based materials and the potential applications in the biomedical and food packaging sectors. So, José, let's hear from you.
Yeah, thank you. As Gabriel kindly introduced me, I'm José Silva, a PhD student in chemical engineering, right at the finish line. So today I'm going to present to you two of the works that I did regarding my PhD, which is through the development of bio-based materials using XYLANS. So here is a brief outline of my presentation. I will be very brief in the introduction, so focus mostly on the results and the conclusions. So, starting with the introduction, as everybody here is fully aware of the components of the wood, and that the Eucalyptus globulus is one of the main species used in the pulp and paper industry, and that they can be isolated into lignins, cellulose, and xylans, and lignin and cellulose already have clear valorization routes, while xylans remain largely underexploited, or mostly they are burned to recover in the form of energy, or in a kind of less volume used to produce furfural or xylitol. But our approach is that we can use these islands to develop more high-value bio-based materials, which can actually be used in functional applications. So today, I'm going to present to you two of the works, one focused on the application in food packaging, and one on the biomedical applications of it. Here, due to time constraints, I won't be able to fully focus on all of the aspects of the work, but if you are interested enough, you can always check. They are already published online, so you can have a more in-depth look of it. So, going to the results. I will start with the food packaging applications. So what we did, we used xylans, cellulose nanofibers, and lignosulfonates, either sodium or magnesium, inspired by the composition of wood. And using the solvent casting method, we were able to prepare different films that you see here. We used glycerol as a plasticizer, and you can see that the films have two distinct colors, but these colors are related to the colors of the lignosulfonates, which you can comprove here to the color parameters that we did, the colorimetric analysis. They are related to the color of the lignosulfonates. So, continuing with the optical properties, due to the presence of the lignosulfonates, we are able to see that all films are able to actually block the UV radiation. So, these films have active properties. They have antioxidant activity due to the presence of the lignosulfonates, but how they behave mechanically. So we did mechanical testing using tensile properties, and what we saw was that, of course, as we were expecting, due to the presence of glycerol, the plasticized films were less stiff. So they present higher elongations, as you can see in the middle graphic on the second part. But interesting enough is that on this last, the tensile properties, they present higher values than the values reported for the low-density polyethylene films that we commonly have at home, that are available on the market, that we have in our kitchens or used to pack a sandwich, for instance. And they are stronger than that. So, as I said in the beginning, we want to have functional materials, not just a whole set of beautiful characterizations. So we decided, okay, how can we test that? And we did fruit shelf life extension tests using pairs. And what we did, we used an aluminum tray. We put our developed films on the bottom, roughly cubed shaped pairs, freshly cut in the middle, and then covered again with our films. And we stored them in the fridge over 7 days, as you can see here. And what we saw is that our films, in the last part you can see, the films packaged with our films were able to delay the browning of the fruit much more. As you can see in the beginning, we have films with no, fruits with no films, and then fruit with the low-density polyethylene film. But our film present the very best results. So we decided to do a whole characterization of the fruit, and we analyze the overall appearance, the browning index, the pH, and the weight loss. And what we saw, starting with the browning index, which corroborates the visual aspect, is that our films, you can see in the bottom, present much lower browning index than the ones covered with the polyethylene and then with the no cover. Regarding the quality of the fruit, more than the visual aspect, we saw that the pH did not change much for our films covered with our lignosulfonate films, while the non-covered and the polyethylene covered present much higher variations. And we also saw that same trend regarding the weight loss. The only exception was that the low-density polyethylene film was still the best in this parameter, but that's regarding the vapor exchange. So this was the first approach where we were able to successfully develop films for food packaging. But now, going for the second application, for the biomedical field, this time we used the xylans in combination with other biopolymer, the chitosan, and we used dipathetic solvents to solubilize the chitosan. And using the same methodology, the solvent casting method, we were able to obtain these films with different compositions that we see here. On the left is films pure of chitosan. On the middle is films 50% chitosan and 50% xylans. On the third column is films with 25% chitosan, 75% xylans. And what we see is that our films, of course, range from transparent to a pale yellow in color, which is related to the content of xylans. And the films with 50% xylans are very, very homogeneous and no bubbles or aggregates are present. When you start to increase a lot the concentration, you can start to see a little bit of aggregation due to the higher content of xylans. So, as I said in the beginning, we want always functional materials. So we have them, we now have to test them. Starting with the mechanical tests, what we saw is that the films containing dipeptidic solvent not only used for the dissolution also as a plasticizing effect, and we can see here in the green bars in the middle that is the elongation. They are more plastic. A good approach, for instance, if we want to apply them in the biomedical field, for instance, as in the elbow or in the knee, they are able to suit those regions. And also they have good tensile strengths, which can actually be used for the biomedical field. Also, just let me add that the addition of xylans slightly decreases the elongation, but still does not compromise it. So, as I said, in the beginning, the addition of xylans increases their color to yellow, which is also related to their UV shielding capacity. Once again, the films with xylans are able to actually shield the UV radiation between the films. So, we have films with active properties. We used chitosan, which is known for having antibacterial activity. And since they are used for biomedical field, we always want to check if they are toxic or not, but we use them for skin applications, so we have to evaluate that, and they are non-cytotoxic. Once again, since the chitosan, as I was saying, the chitosan is antibacterial, we did tests with that too, and we did tests in vitro, and the most interesting part that we saw in this test was that, I'm not sure if you can see from over there, but the third from the bottom, which kind of has a brownish color in the graph, is the film with 50% xylans, 50% chitosan, while the other ones in the bottom is 100% chitosan. This means that we are able to achieve a 50% chitosan reduction while maintaining similar kinds of antibacterial activity. This can be a huge economic opportunity for reducing the cost in chitosan. But still, these are very good results for antibacterial activity. But this is an in vitro test. We wanted to go further and did an ex vivo test. We used porcine skin contaminated with the methicillin-resistant Staphylococcus aureus, which is a common strain in hospitals and those kind of environments. And we saw the same results. The best performing film, once again, was the one that has chitosan, dipeptidic solvent, and 50% xylans, which is the best results that we got so far. So we decided, okay, they can be used as an alternative for currently existing biomedical materials, but can they go further? And we decided, okay, let's test how is their wound healing capacity. And so we did scratch tests, which are in vitro, which consists of have an even layer of ACAT cells. Then we did a scratch to simulate a wound. And then we had an extract where our films were previously in 24 hours to the extract. And then we had that. And what we saw, once again, on the not the last column, but the second from last, on the bottom, is that after 30 hours of contact, we are able to have a 76% reduction of wound areas, so we have more closure. Okay, once again, we are like, okay, this is good, but we don't want good, we want great. So not only we did two-dimensional testing, we also did a 3D wound healing test. What we did basically was using a gel and gum hydrogel embedded with ACAT cells, where we cut the middle off, so to simulate a wound once again, and then covered again with the gel and gum, but this time without cells. And then we applied our film this time. And what we saw is that after 72 hours, we are able to have an increase of 17% of relative cell viability within the range where there were no cells in the beginning. So we are able to prove that we can actually have a material that promotes wound healing and cell migration. So this was very quick, a lot of results. So just to conclude, what I want you to take from my presentation is that using xylans to develop materials is possible, and we can use them to add value to these resources. They are not just byproducts to be burned or disposed. We can use them. And once again, xylan-based materials can be an alternative or even an improvement to the ones that we currently have in the market. And this, once again, it represents both an economic and environmental opportunity. We can help us go forward towards this more circular bio-based bioeconomy. So before I go, I leave you with the beautiful images of Aveiro, my university, and I just want to thank again everybody related and everybody in this work in this project, my supervisors, and Selby and the Navigator company for funding my PhD. So thank you.
Thank you, José, for a very nice presentation, very exhaustive, and also in line with you, not only good timekeeping, but also great timekeeping. So thank you for that. We're going for the next and final presentation then. We're going to delve into the world of carbon capture and green methanol production potential in the pulp and wood panel industries. So this presentation is being presented by Raimon Marin. He has more than 14 years experience in the syngas and refining technology area, where he has developed several roles from engineering to technical sales in ammonia, methanol, and hydrogen. So Raimon works for KBR and holds a technology manager position in the green ammonia and methanol, helping KBR clients defining plant configuration and activities required to close the final investment decision. So Raimon, the floor is yours.
Thank you very much for your kind introduction. So yeah, be ready for a change again. I will be talking about carbon capture and methanol production. And there is a reason for that, and that is pulp mills have abundant biogenic CO2. Biogenic CO2 is the enable to produce methanol. You need biogenic CO2 to produce methanol, and pulp mills have that in abundance. And nowadays, they do nothing with that. So this is a value proposition for the pulp mills to look into alternative routes to valorize their CO2 emissions. So first, let me introduce what one of the things we do in KBR. KBR is an engineering and licensing company. That means that we do engineering, and we also provide technology. We have been doing that for over 80 years. We are world leaders in technologies for fuel, agricultural, like fertilizers and petrochemicals. Thanks to that, we are in a very good position to also offer renewable routes to conventional products. So, for example, ammonia or methanol, that's what we will be talking today. Again, to produce methanol, we need to capture CO2. For that, we also have a technology which is called K-CAP, as we can see in here. All right, so let's move into methanol. I'm not sure how familiar you are with methanol, but methanol is a commodity chemical, have been produced massively in the last 80 to 100 years using two main routes. One is natural gas reforming. So you take natural gas, you reform it, you produce syngas, and then you produce methanol. Most of the methanol produced nowadays uses that route. Alternatively, you can also use carbon. You gasify the carbon. Again, you produce syngas, and then you produce methanol. Today, or maybe last year, 110 megatons of methanol were produced worldwide. So you may wonder, what is this methanol for? Methanol is a building block. From methanol, you start producing other chemicals like solvents, adhesives, and day-to-day chemical products. Also, it is used as a fuel, either as a blending fuel. For example, in China, it's very common to add up to 10% methanol into the gasoline. So you use methanol as a fuel in your car. It is also used to produce fuel additives. In the refining industry, methanol is used to produce those gasoline additives that they end up in your car. Where methanol is produced nowadays, mainly China. What a surprise. So more than 50% of the world production of methanol today is China, and then Middle East and a little bit of USA and other countries. Carbon intensity, key parameter today. If we produce methanol from natural gas, it has a relatively high carbon intensity, but nothing compared to when you produce methanol from coal gasification. Those are large quantities of CO2 we emit by producing conventional methanol. As I said, there is a massive amount of methanol produced nowadays with those CO2 emissions. Now, if we are to produce renewable methanol, for example, using the CO2 that is an outlet in the pulp mills, it's just vented from the recovery boiler or a biomass boiler, we can reduce the CO2 emissions by a tenth to somewhere between 10 and 25 grams per megajoule of methanol produced. So there is a big potential of cleaning the industry, the methanol industry, by using the CO2. So as I said, why renewable methanol? Well, if you look at the IMO, the shipping industry, is looking into methanol as a shipping fuel. Nowadays, there are more than, I think it's around 200 ships worldwide, big containers, that they have dual motors, so they can either use heavy fuel oil or methanol as a fuel to carry things from one part of the planet to the other. And also, as I said, as a gasoline additive that can be used, is used today, but we can clean up this industry by using renewable methanol. And again, as I was saying before, methanol is a building block. From methanol, we can make other chemicals, like, for example, formaldehyde. We can do olefins from methanol and produce all sorts of day-to-day chemicals. And obviously, will also help the enterprise sustainability goals. So why in the pulp and paper industry? As I said, plenty of biogenic CO2 available in the pulp and in the recovery boiler or biomass boiler, if there is any. Pulp mills, they also have plenty of steam. To produce methanol, you need a little bit of a low-grade steam, so there is a good synergy in there. Methanol can be used in industries nearby to pulp mills, if there is a need for formaldehyde, for example. And just to reiterate the large amount of CO2 that we have in the pulp industry. Okay, so let's have a look to how we would produce methanol, starting from CO2 recovered from a pulp mill, for example, or from biomass, say. So we have the biomass. In this case, we represent that it goes to a biomass boiler. CO2 is produced, basically in the flue gas. We can use K-Cap. K-Cap is KBR's technology for carbon capture to extract the CO2 from the flue gas. Then we have pure CO2, and nearly pure CO2, that we can use in the methanol process, right? a parallel way, we also need hydrogen. If you remember, methanol has 4 moles of hydrogen per mole of carbon. So we need hydrogen. And it has to be renewable hydrogen, so typically that would come from electrolysis. So to produce hydrogen from electrolysis, you need 2 things. One is water, which is quite easy to get. The other one is renewable power. Again, along with CO2, you need this process to be located in an area where you have plenty of low-cost renewable power. Once you have the 2 main ingredients, you can then produce methanol using a PUREM process. And the methanol, as I said, can be used as for chemicals or fuels. If you look in this box in here, I listed methanol. Methanol is the same, rather. It doesn't really matter if you start from coal, natural gas, whatever. Methanol is methanol. But we specify, or we list it as 3 different types of methanol: biomethanol, bioethanol, e-methanol. All of that is just to define how you get to methanol, right? All of that will define all of this part in here. Okay, so some characteristics of the CO2 that we will take from the biomass boiler. So the CO2 is around 8 to 12%. Typically, the higher the amount of CO2, the easier is the recovery process, right? And then just looking into the stoichiometry of the process, you need around 1.4 tons of CO2 per ton of methanol produced. Similarly, 190 kilos of hydrogen per mole of per ton of methanol you produce. So that equates around 9 to 10 megawatt of electrolysis. Electrolyzers you will need to produce the hydrogen. So now what we are going to do is to break down this scheme in here and look into the 3 main processes we have, right? The K-CAP, the KBR carbon capture process, the electrolysis, and the PUREM, again, the KBR methanol synthesis process. So if we start with the K-CAP. K-CAP is a conventional amine process to recover CO2. Amine process to recover CO2 or acid gas is an old industry, have been used for many, many years, mainly in the refining industry and also in the gas processing industry. Basically, you react your acid gas, can be H2S or CO2, in this case is CO2 with an amine solution, and then you extract the CO2 using this amine solution, and then you dissolve the CO2 from the amine, and then you recover the CO2. So we do that using this scheme you see in here. So basically, we start from the flue gas stack, the recovery boiler or biomass boiler, whatever it is, and then it goes into the DCC, so it's the direct contact cooler. We cool down the gas to around 40 degrees, more or less, and then we remove other impurities we don't want in the process. And then we go into the absorber. The absorber that we do in KBR is a rotary bed package. Typically, that would be a very big column, but we can do that using intensive process, which means that we do the process in a small compact unit. So we can both reduce the capex, the cost of the unit, and the footprint by using this rotary bed package. So in here, what we have is lean amine that will absorb the CO2 from the flue gas that is coming in this way. The depleted flue gas, so that means flue gas without CO2, will be vented. That's mainly nitrogen. And then the loaded amine, so amine plus CO2, will go all the way to the desorber. In the desorber, by means of applying heat, using low pressure steam, we desorb the CO2, and then we recover the CO2 with a very high purity up here, more than 99% CO2. So starting from 8 to 20% CO2, we are able to get a pure CO2 that will be later used as feedstock for the methanol process. So now we have the CO2. So let's, this is just a representation of the rotary bed package that I was describing. So it's a compact unit, again, that reduces both capex and small footprint, That's very important, especially for existing plants. Existing plants tend to be already packed with a lot of units and equipment. So typically you don't have much space to deploy new units. So having plants or units that have a very low footprint is beneficial for the implementation of this technology. So now that we have the CO2, let's produce hydrogen. Hydrogen, as I say, typically comes from electrolysis. For electrolysis, you need electricity and water and an electrolyzer. Electrolyzer is a piece of equipment that using the electricity and water will produce the hydrogen. Today, there are two technologies that are market ready. So they are already used in the industry to produce hydrogen, alkaline and PEM, which are the two you see in here. And solid oxide electrolysis is also coming up very fast. It's much more efficient than alkaline or PEM, but still lagging behind in implementation. So I won't spend too much time in the electrolysis, but basically that's how you produce the hydrogen. So now we have the two main ingredients to produce methanol, CO2 and hydrogen, and then we go to the methanol plant. Methanol plant to produce renewable methanol or e-methanol, which is called when you have electrolytic hydrogen, is essentially the same plant that you use to produce methanol from natural gas or coal gasification, if you recall the conventional way of making methanol today. So there is very little changes. That means that the technology is proven, has been used for nearly 80 years, it's reliable and solid and just works. There is nothing really new besides small tweaks that I will mention now. So we have CO2 and hydrogen. The first thing we do is we remove some traces of SOx, typically coming from with the CO2. We don't want any sulfur species going to the methanol converter because that will kill the catalyst. So we want to remove that. So we do that in here. And then we compress the hydrogen and CO2. Methanol is produced at high pressure, around 80 bar. So we need a compressor to bump up the pressure. So the feedstock, which is the CO2 and hydrogen, go into the methanol conversion section. In there, we have the converter, the reactor, loaded with catalyst. Catalyst is typically copper zinc catalyst. We put the CO2 and hydrogen over the catalyst, 80, 90 bar, around 200 degrees. We produce methanol. Methanol and water, equal amount of moles. Along with that, a lot of heat is produced. The reaction goes to equilibrium and then stops. That means that we don't convert all the CO2 and hydrogen per pass of converter. It means that we need to recirculate the CO2 and hydrogen because we don't want to waste that feedstock. We do that by decreasing the temperature, condensing the water and methanol, and some byproducts we also make along, and then disengaging the unreacted hydrogen and CO2, and then we put it back at the front. And then it goes around till it gets fully converted. Now, as I said, the reaction is exothermic. That means produce heat, a lot of heat. We use that heat to produce steam. And that steam is used later on in the distillation. In the methanol converter, methanol, water, and byproducts are formed, but we only want methanol. How do we recover methanol? By doing distillation, typically in 2 steps, maybe 3, sometimes 1, depending on the technology. But basically in the distillation, what you do is you separate the water, the byproducts, and then you recover the methanol, which is your product. As we all know, distillation works with heat. In the industry, typically steam is used as a heat source for distillation. We use the steam we produce in the methanol converters to do the distillation, but there is not enough steam. We don't produce enough steam in the converters for the distillation. 3 minutes. 3 minutes, okay. Yes. I like to talk about this. Right, I'll be very quick. So we need to either import steam or modify the design for that purpose. And then we produce the methanol. Okay, so I have a case study that I will fly through. basically showing the economies of producing methanol. So we start from a flue gas, from a biomass boiler. It's a relatively large flue gas quantity, and then we define 4 different cases, 4 different methanol production capacities. The methanol will set the amount of CO2 we need, and that will define how much flue gas we require. Equally, the methanol will dictate how much hydrogen, and that will say how much renewable power we need to produce that hydrogen. And we do it for 4 different plant capacities, right? Since a small plant to a large plant. So we can see that we have plenty of flue gas in the biomass boiler we took as an example. Now we look into the economics of that. So if we look at the CO2 we recover, in here we can see the price of CO2, so dollars per ton of CO2 for the 4 different capacities we have defined. And here we have the levelized cost of methanol, so the cost of production, and the hypothetical price of CO2 if we want a 15% return on our investment, right? So we can see that the levelized cost of CO2 ranges between 50 and 100 tons, which is something that we all may expect if we have looked into this into the past. The other important thing, these carbon capture plants are subject to economy of scale. That means that a plant of, for example, 200 tons per day will not cost you double than a plant of 100 tons per day, but somehow a little bit less because we have this economy of scale effect. If we look at the hydrogen cost, hydrogen is mainly driven by electricity cost. So what we have represented here is the power price, electricity price versus the hydrogen price that will be basically driven by this price. Electrolyzers doesn't suffer of economy of scale because it's highly modularized technology. So it's like packs that you just pay for as many packs as you have. And finally, if we look at the methanol costs, again, e-methanol cost is basically driven by the hydrogen, which in turn is driven by the cost of electricity. So cost of electricity will be the main driver of your methanol. CO2 is enable you to make methanol. Electricity will set the cost of your e-methanol production. So just some examples, if you look at the conventional methanol cost, FOB, like a free on board in Rotterdam for 2024, it was between 450 and 600. If we have a electricity cost around $25 a megawatt, you might not be too high. But again, that price is excluding any carbon penalty. So once you add the carbon penalty to that price, you might not be too far if you have a low electricity price. So how to make use of that? So one of the things we can do in the pulp industry is leverage access of biogenic CO2 and renewable power, and then offer a methanol, a product that can offset the carbon penalties that may come with it. Some conclusions very quickly. The technology we offer at KBR is already proven, is in operation. So we are ready to design and provide guarantees for those processes. The pulp and paper industry, as we said, there is plenty of CO2. In some regions where pulp and paper industries are predominant or abundant, like Scandinavia and Latin America, we have another factor, which is low-cost renewable power. So in those specific regions, producing key methanol can be very, very attractive. I think that's some of my colleagues. If you have any questions about methanol technology in KBR, just give us a ring or drop us an email. We are more than happy to talk to you about that. So thank you very much.
Thank you very much. So we have a couple of minutes for some Q&A. So I'll open the questions to the audience. Hopefully we get some curiosity on the public attending. Any questions? This one here, please.
I have a question to the first speaker. So, which are the methods did you use to measure the sugar? Because you're talking about the SMEs, and that's a mix between lignocellulosic and fungal biomass. So, what is the method that you used to measure that sugar?
Yeah, I don't know if I'm audible right now. Yes. Yeah. Okay. First of all, thank you for the question. I think that at least in the how part, perhaps in the essence of time, I omitted some details. The way that we quantify the sugar content in all experiments is actually via HPLC. We use a specific column in this case, that is the HPX87H column, that we have calibrated in order to quantify very efficiently some sugars. We have focused, of course, in glucose and xylose, but it is possible to determine the presence of other sugars if needed. And we actually use that system, the HPLC, not only for this type of experiments, but also when we are moving forward and basing fermentations on it for the consumption of carbon sources and also for the presence of some organic acids. But yeah, in short, HPLC.
Another question there, please.
Hello, thank you so much for the presentations and also for the first speaker, Luis. How did you make the recovery of the lignin from the valorolactone?
Oh yeah, of course. Thank you for the question as well. In this case, it's mostly getting rid of the solvent first, and making sure to do it in a manner that the lignin that is left behind faces as little degradation as possible. Because in the case of the presentation, what I tried to make evident is that when you use either gamma-valorolactone or other solvent, the lignin that you recover, of course, is going to be degraded to some extent. And also, when you use different proportions of solvents and different conditions, this may also impact the final quality of the lignin. But in this case, it was mostly recovered by getting rid of the solvent. And there's one additional thing, and it was not shown in this presentation, but we have carried out some characterization of the lignin that we have recovered. And this is actually very important because as opposed to the lignin first approaches, sometimes these kind of approaches deal with lower quality lignin. And that can pose a disadvantage if you do not do this step carefully. So yeah, that's actually a very nice question. Thank you so much.
Another question from Harry here on the right-hand side.
Yeah, thanks for the interesting presentations. I have a question to the last. So first of all, myself, Henry Oppola from Andritz. Regarding these biomass boilers and its usage for integration to this methanol production, is electricity produced from biomass, is it considered appropriate for this e-methanol production? And then considering the typical size at a modern major pulp mill, it would be around 20, 30 megawatts at max. Is that enough of electricity for the electrolyzer?
Well, first, thank you for the interest. The answer to the question about if electricity from a biomass boiler would qualify as a e-methanol or to produce renewable methanol, the quick answer is yes, it will qualify basically because the carbon intensity will be nearly zero. The second question, if I understood right, is if 20 or 30%, 20 or 30 megawatt electricity is sufficient to run the electrolyzers.
Yeah, and considering the graphs you showed about the economies of scale,
yeah,
because they are not that big.
No, if you recall, around 60 megawatt will give you a plant of 140 metric tons per day in methanol. half of that will be around 70, 75 metric tons per day of methanol. That is considered a very small methanol plant. Now, economy of scale is one thing, right, when we are talking about a large production of methanol. If, of course, you can make a plant of 70 or 75 metric tons per day of methanol. The economy in that scale is slightly different to when we play in the large capacities, but we can design a simpler methanol plant that may not be as efficient as the large plants, but in small plants, the capex is more relevant than the opex, right? So for the small plants, we would design a much simpler converter, for example, and a much simpler steam system and distillation system that will make, may not be the methanol production cost as low as plant of 1,500 metric tons per day, but still competitive.
Thanks. One final question. What about recovery boilers using black liquor from the pulp mill? Is that considered
CO2 would qualify as a RFNBO, yes.
Yeah, and also the electricity?
Of course, yes.
Okay.
As long as it's not fuel-based, it will qualify. Basically, when we talk about methanol as a fuel, there are two standards, the IMO for a shipping industry that last week had a bit of a step back or hold on, and then the RFNBO, the European Union directive, the RED 3. CO2 from a black liquor from a recovery mill would qualify as a RFNBO, and electricity produced in a pulp mill will also qualify for RFNBO.
Good, so I apologize, but I'll have to cut off. We already run short of time, so thank you a lot for the very nice presentations and Q&A interaction with the audience. It was very interesting to be here. Before we dash off, so we have lunch happening on between 1:10, which is already gone, and 2:20 p.m. That will be happening on the hotel restaurant on the floor 0. I will encourage you to be back on the rooms before the 2:20 p.m. so to start the sessions in time. So finally, just final thank you and final round of applause to our colleagues. Thank you.